Now let's look at this example as an application on Bernoulli's equation. All right, assume that we have some kind of an artery in someone's body. This is an imaginary one. And assume the artery looks like this. Okay? There is a certain surface area here. I'm going to call it A1. And a certain surface area here for the opening of the artery. I'm going to call it A2. Now A1, so A1 is unknown, and A2 is equal to 0.33 A1. Okay? And blood is flowing this way. All right? Okay. So the distance the blood goes up here is 0.7 meters. The velocity of the blood at the lower end is equal to 0.65 meters per second. The velocity here at the top, we actually don't know what it is. Okay. At the bottom, the pressure is unknown, and at the top also the pressure is unknown. Okay. The question is, as we mentioned before, is to find the pressure difference between the lower end and the upper end. So that's what we need to find. There's a blood flow. So the fluid is non-static, and we're asked about pressure difference between the bottom and the top part, and there is a height difference when the artery starts and where it ends. So that's a good application of Bernoulli's equation. Bernoulli's equation says that the pressure P1, this is, I'm gonna say this is spot number 1, and this is here spot number 2. So the pressure P1 plus 1/2 rho V1 square, which is the density times the velocity squared at this part of the artery, plus rho GH1, which is the density times the gravity times H1, which is here, is equal to P2, the pressure at this area here, plus 1/2 rho the velocity at this area here, V2 squared, plus rho GH2. So we are applying Bernoulli's equation, as you can see. Okay. Now the problem is asking us to find the pressure difference between the lower and the top part. So I'm going to take this part here, P2, and put it here. So this whole thing becomes P1 minus P2, because that's what the problem is asking us to find. So this is actually what we are looking for. So we took P2 to the other side, becomes minus P2. So P1 minus P2 plus, I'm going to continue here, 1/2 the density of blood. I'm going to give you the density of blood. There it is, 1060. The density of blood is equal to 1060, okay, times V1 squared. Do we have V1? Yes, we do. 0.65 square, plus, now rho G H1. H1, if you pay attention, you can see that this is the reference level, and the reference level can be considered at height equals to 0. So this whole term, actually, I'm going to put it equals to 0. So this whole term goes to 0. So plus 0, okay, is equal to P2 went to the other side, 1/2 times the density of blood, which is still 1060 at that height, V2 squared. We don't have V2, okay, so I'm going to leave it here, plus rho, which is 1060, times 9.8 times H2. H2 is at the height 0.7. Okay, now let's look at our equation. We have in our equation actually two unknowns. This one and this one. And this is one equation with two unknowns. We cannot solve it. So we have to look for another venue. And the other venue comes from the continuity equation, which is density rho 1 times the velocity 1 at this point times the surface area at this point of the artery is equal to rho 2 V2 A2 at this point. Okay, perfect. Now, since the density of blood does not change, you can divide by it or cancel it out. Okay, so you end up with V1 times A1 is equal to V2 times A2. Now, V1 is given 0.65. Okay, A1 is actually not given, so it's going to come down as A1 is equal to V2, which we need to find. Now, A2 is given by, or in terms of A1, which is 0.33 A1. Now divide by A1. A1 with A1 goes away, and once solving, then V2 ends up to be equal to 1.97 meters per second. So that's the velocity of the blood at this opening. And it makes sense that it is faster because, as you can see, the artery tapers down, becomes narrow at the top end here. Okay? So now let's plug V2 here and make some calculations. So P1, so I'm going to come down here. So P1 minus P2, which we are looking for, plus, now this term, after we do some calculations, it becomes 223.9 is equal to this term. After we plug in V2 squared it becomes actually 2056.9, and this whole term after some calculation becomes 7271.6. and as you can see, this is one equation with one unknown. Take this, add these two parts together and subtract this one from it, and you can find that P1 minus P2 is equal to 9,104.6 Pascal. Okay, that's a pressure. Now P1 minus P2 is positive, as you can see. This means that P1 is at a higher pressure than P2, and that happens for two reasons. First of all, P1 is a higher pressure because it's a lower level. Okay, that's one. And the second part is that it's the speed of the blood here is much less than the speed of blood here, so the pressure here is higher, and that makes sense. Okay, that's it for this problem. Thank you.